Good morning and welcome to everyone who's joined us today. My name is Chris Evans and I'm Marketing Operations Group Director here at Mitsubishi Electric UK. As we continue through our We Know series of webinars, today we're looking forward to sharing with you what we know on collaborative and cooperative robotics. During the session, if you'd like to ask a question, you can do so by using the control panel found in the top right of your screen. You can minimize or expand the control panel using the red arrow at the top. We will answer as many questions as we can at the end of the session. Any questions that we do not get a chance to answer, we will answer by email after the webinar. So I'm now going to hand over to my colleague, Barry Weller.
Thank you, Chris. Good morning, everybody. I hope everyone's keeping safe and well. So my name is Barry Weller. I'm the Robot Solutions Manager here at Mitsubishi Electric. And today I'm going to be presenting on collaborative and cooperative robots. Before I start, I'm just going to update you on the other series of presentations within the We Know webinars. So this is actually the third presentation. We've already done two. First one was on cybersecurity and the second one was on edge computing. These are actually still available online. So if you follow the link that you can see in the bottom left-hand corner here, you can gain access to those two webinars. As I said, this is the third one on collaborative and cooperative robots. Next week, we've got one on predictive maintenance. And then following on, we've got two more scheduled in on smart manufacturing and then compact control and safety for OEM machinery. So if you want to register for either of those three webinars, again, just please follow the link below and you can do that through that method. And again, this broadcast will be available to view again if you wish at that same link. So today's topics we're going to cover is just really a quick overview of the different types of robots that are currently available, and then have a look at how these robots can be used in a mix of industrial, collaborative and cooperative applications. To do that, we also need to consider some of the standards that are applicable. And then the best way of getting the messages across really is through worked examples. So we're going to go through a simple application on one that we commonly see. We'll then look at a few of the other spectrums of applications and which type of robots can be best suited and which type of technology is best suited there. And then to roll out the presentation, we're just going to have a look at the future technology and how digitalization can help with this environment as well. So to start with, we're going to take a quick look at the industrial robot sector. So there's a huge variety of different shapes and sizes of industrial robot arms. For instance, here at Mitsubishi, the MELFA range of robots, there's over 200 different models to choose from. So I'm just going to go through a few of the different types we've got available. I'm going to start with the SCARA robots. SCARA actually is an acronym. It stands for Selective Compliance Assembly Robot Arm. And these arms are usually found in high precision, high speed pick and place applications and packaging applications. Moving on from that, we tend to find Delta robots. Now these are usually uniquely found in high-speed packaging lines where you need very high productivity rates, and there's usually a few of these lined up in a row doing that high-speed packaging application. And probably the most common type of industrial robot arm is the 6-axis or vertical robot. And these are the most common because they're the most versatile. They can pick up the component not just in an X, Y, and Z orientation, but they can also manipulate it in free space, doing pitch, roll, and all. So that gives the process as much flexibility and future-proof as possible. So typically with an industrial application, they'll be enclosed within a cell or within some safety guarding. So here I've given you a quick picture of a typical robot application, where the robot is really the heart of the process. It's there to manipulate the components, and often it's to remove the operator from that particular type of environment. So these jobs tend to be the dull, the dirty and the dangerous jobs that you want to remove the operator from. And they're famous for their high speed and flexibility in the assembly process, and also their high repeatability, giving good quality manufacturing processes. There are a few myths, though, that have been disbanded about industrial robots. So I'm just trying to tick a couple of those off now. The first one really is industrial robots are onerous to set up. Well, this isn't actually the case. All of our robots come pre-calibrated. They're ready to be powered up and then placed into the machine, and then you can start programming them. So it actually can take less than an hour to connect up and get to that stage of where you're ready to start using the robot. The other myth is they're quite expensive. Well, actually, again, this isn't true because there's such a wide variety of robots, particularly that lower end, that SCARA end of the marketplace. You can actually buy a very competitive industrial robot arm and use that in any kind of application you need to. So where do collaborative robots sit in? Well, this is really a bit of a disruptive technology. These are designed to work without that guarding around the robot arm. They're designed to work hand in glove with the operator. And they're really there to aid the operator in maybe part of the assembly process. And it's there to remove the physical barrier between the robot and the actual process and the operator to give that extra flexibility. So here you can see a picture of the MELFA ASSISTA robot arm. And what you'll notice with the collaborative style of robots is they tend to start looking a similar sort of design concept behind them. Now, a lot of this is dictated by a standard ISO TS 15066, where the standard tries to guide manufacturers to designing a robot arm that has certain factors to make it safer to be around people. So these are things such as having no pinch points. So if the hand does get trapped between two joints, there can't be a scissor action, a pinching action that could damage that operator. There's also other functionality to help minimize any collision or any damage or injury from a collision. So these are things such as speed limiting. There'll be a rounded shape to the appearance. So if there is a collision, the collision impact point is spread as wide as possible to minimize any high intensity zone of that impact. And then some kind of measuring device that's going to detect that collision and then put the robot into a safe mode of operation, i.e. it's going to stop the robot before it's done any serious injuries. The other brilliant function, or the other advantages of the collaborative style robots, is it's introduced a new style of programming. So here you can see our RT Visual Box programming tool, and it's designed to be very graphical and very easy to both program and also look at the programs. So you can see a nice flow diagram where you'll see images to reflect each type of movement. So for instance, the move instruction, if I double click on that on the computer, it will bring up a dialog box. And this dialog box will have a sort of a wizard style interface that will let you select the type of move you're going to be doing and enter in common information such as the coordinates the robot needs to move to, or you can teach the robot those coordinates. If I look at another instruction like the branch instruction, again, that will bring up a dialog box that will make configuring the condition at which that branch will occur as simple and as easy to use as possible. So I see there's a perception that there's two types of robot arm out there. There's two types of application. There's ones where there's no human interaction, which is the industrial arena. And then there's one that's the assisted working or the collaborative area of operation. But the reality is a bit different. There's actually lots of overlaps within the two opportunities where you might want an industrial robot for its speed and accuracy or repeatability, and you want a little bit of collaboration with the machine loading and unloading components. So there's this middle area where you can use a choice of two different technologies. And what we do is we call that area the cooperative arrangement. This is where you can use an industrial robot in a collaborative way of working, or likewise you could use a cooperative robot in a more of an industrial style application. So where does this come from? What is the foundations for this? Well, all of it is within the standards. So we need to start looking at the actual standards that cover the industrial robot world. And with any machine, the machinery directive is the overriding standard. So here I've put a definition up of what a machine is within the machinery directive. And it reads that it's an assembly fitted or intended to be fitted with a drive system other than directly applied human or animal effort, consisting of linked parts or components, at least one of which moves and which are joined together for a specific application. Okay, so that really defines what a robot for me. It's a mechanism with fixed joints and a drive system, but out of the box it doesn't have any specific application. So it's what they call an incomplete machine, as it has no intended use until it's been integrated inside the process that it's intended to use. It therefore isn't intrinsically safe, and it doesn't carry necessarily a CE mark under that machinery directive. So that means robots have a standard that they adhere to, the ISO 10218, and this is in two parts. One is for the robot manufacturers such as ourselves to deliver a system that's certified to be used with safety certain functions. The second part of it is aimed at the system integrator to implement those safety functions as safely as possible within their particular application, and then risk assess it to that. Now, this standard's been around for a few years. I've put a note here to say it was updated in 2011. This was really preceding a lot of where the advancements have come now with collaborative robots. The standard does make reference to collaborative working, but doesn't really go into the details. So there's some substandards that have been written, some technical revisions or some technical specifications that have come out since. So a couple of those I'm going to look at. Firstly, just an overview. There is one, 20218, which is designed to help guide a system integrator on the safe implementation of using safe grippers with collaborative robot arms. So this makes recommendations such as the force the gripper can apply, the size, the shape and design of the end effector, so there's no sharp points, and this minimises the damage between the end effector, the workpiece, and also the operator. The one that is more interest to me as a robot, a product manager, and also from a robot's perspective, is TS15066. So this is a technical specification that is designed to help guide system integrators to put together a collaborative working system. And it's got a few recommendations and guidelines, which we're just going to cover in a bit more detail now. So the specification lists 4 different types of application. So these are hand guiding, safety rated stop, safe speed separation monitoring, and power and force limitation. And what I'm going to do now is just cover each one of these topics in turn, just giving you a bit more information about how they're typically used. Starting with hand guiding, well, this is where the operator will take the end of the robot and he will guide it to a position for a teach point, for instance. And this actually could be used for any type of robot. The standard recommends there's a 3-position enabling device, and it's probably better that there's 2 operators doing this activity. One operator is moving the robot to the guided position, while the second operator is safeguarding that operator's actions with this 3-position enabling device, making sure that there's no collisions or no injury occurred in that process. The second is safety rated stop. So this is where the robot can work unguarded. However, the working envelope that the robot can work in and the operator. So the idea here is that the robot has to be stationary if the operator comes within the working envelope of the robot. So often you'll find some kind of soft guard in an area scanner or a light curtain that is there to protect the working cell around the robot. And if the operator comes within reach of the robot's working area, the collaborative working space or the cooperative working space, the robot must be stationary, must have stopped. That's where it gets its name from, safety rated stop. So there's obviously another few standards that come into play when you start looking at this. The positioning of that light curtain away or area scanner away from the robot arm has to be of a safe distance to have activated completely before the operator comes within that collaborative working space. So that's another standard for light curtains, which is 13855. So safe and speed monitoring, well, that's actually a variation on safety rated stop. So this is where, as the operator approaches the robot's speed slows down until eventually the operator resumes that cooperative working space. And then the robot must be stationary. So again, an area scanner is generally used for this type of application that's going to detect the operator coming towards the machine, coming towards the robot. And the robot gets slower and slower depending upon the distance until eventually it has come to a stop. So that can also mean there's quite a big area footprint of this type of installation, again, to cover this fact that the robot has to have stopped safely before the operator is within that collaborative working area. And the final one is power and force limiting. So this is what most people consider a collaborative working environment. This is where the operator and the robot are working in the same space continuously. Because of this, the robot is moving within proximity of the operator. So there needs to be some kind of prevention that if there is a collision, that the robot stops to minimize any kind of injury. So this is where we start employing technology such as safe positioning, safe speed and force limitation. And again, the rounded design and no pinch points on the robot come into their own to help minimise and prevent those injuries occurring. So the question really I'm going to pose is which one of these robots that you can see pictured here can be used in a collaborative application. Okay, and not surprisingly, all of them can be. And why do we say that? Well, the safety rated monitoring stop, safety speed separation, and hand guiding. Well, actually, the robot is stationary where the operator is in the collaborative working space. So this can be achieved with any industrial robot arm. Whereas the power and force limiting, that's where you need to start using the collaborative style robot arm. Again, it's got those built-in functionalities to limit the power and the force, so therefore it's safer to allow those impacts between the operator, and there's no trap points. But the big difference really is, well, the robot is operating without the robot is running without the human around the environment. They can obviously run at a lot higher speeds because they're designed for that speed application, and also that higher precision, those higher accuracies. So why do we use robots? Well, industrial robots are usually there to increase the speed of production and increase the production quality because of those factors I mentioned. Because you're producing better quality products and you're producing less scrap, you're going to use less raw materials in the production process, which is going to make it more efficient and bring the price of the product down. It's also going to reduce any errors from repetitive tasks where human operators may get bored doing the same process continuously. The robot never gets bored, doesn't take breaks, runs 24/7 with no issues at all. Whereas a collaborative robot, well, that's designed to help the operator actually to be more efficient with their job. So they might be coexisting in the same workspace, doing the same tasks. And this can help reduce any kind of RSI type injuries where the operator is continually doing the same pass continuously. The robot can do those continuous tasks and the operator can focus on the tasks that are slightly more dexterous that humans are excellent at. It's not just the robot that we have to consider, it's also other elements such as the workpiece that we're picking up. If we're doing a machining application and we're making razor blades, it's obviously not safe to have that razor blade free in the tool without any kind of guarding to protect the operator. There's no way you could safeguard against that type of impact. So the standard will also make some recommendations against workpieces with sharp edges, particularly heavy workpieces. Maybe if it's a hot temperature, but also a cold temperature for the workpiece, and any kind of toxins within the actual product that you're manufacturing, such as in the pharmaceutical laboratory. Other points to consider is the environment. There might be some fast moving parts of the machine away from the robot arm that they will need to be safeguarded against. The operator needs safeguarding against. If you're doing a sanding application, is there any dust produced that you actually want to protect somebody walking past the process from, not just the person that's actually working with the robot? And painting and things, obviously, that will give off some toxic fumes into the environment. Again, you want to try and reduce these as much as possible. So what I'm trying to say is the guarding doesn't just protect the robot and the operator from the process, but also the environment the robot is working within. So what I'm going to do now is just go through a quick application example. And this is a typical request a customer will come in and talk to us about. So they'll usually come to us with a vision. So in this instance here, the customer's got the vision of they want to automate a machine tending application. So they've got some kind of machine. The robot needs to load a component into. The machine will do its machining on that component, and then the robot will unload that first component and then load in the next component. And the vision the customer has is they just want to place a robot next to a pallet containing all of the parts to be processed and the robot to load each one in turn. They want to have the minimum footprint possible, so they've decided to go with a collaborative robot. They also want that because of the easy programming and easy flexibility. So they're looking at an application that's using power and force limiting. So one of the limitations straight away is the speed of the process. The robot is going to be limited to the speed, the maximum speed it can run at is 250 millimeters per second. So the first thing we do is try and help the customer is we run some kind of simulation. So here you can see a picture of the simulation that we did, where we placed the robot in front of the machine. and then we had the robot move in and out, and then we calculate the cycle time. So the two advantages we get from the simulation is, one, we know that's the right size robot for the application. We know the robot can reach all of the necessary components and all the areas within the machine. And then we know the rough cycle time, so the customer has a feel for the throughput that machine can operate. We timed the operator loading and unloading components, and it takes about 8 seconds. And then we did the cycle time analysis. We do it for the collaborative robot in a power and force limitation mode, which limits to 250 millimeters per second. That came out about 16 seconds. That's about half the speed of the operator can process at. In full speed mode, in the more speed and separation monitoring modes, its maximum speed is 1,000 millimeters per second. So again, so it's about 9 seconds for that process. And you can see here, the operator is still actually slightly faster. And then finally, we looked at the industrial solution, which was just under 4 seconds. That's 50% faster than the operator was. So that's going to give you the most throughput of the machine. And these factors really is totally down to the application of which is acceptable to the customer. But there is another point to note, and the point to note is, with an unguarded robot, you have to consider the type of impacts that might occur on that process. And within TS 15066, it mentions 2 different types of impact. One's a transient contact or free impact. This is where the robot will collide with the operator, and the operator can recoil or move backwards, minimizing the length of time of the impact and also the intensity of the impact. So these impacts tend not to be the ones that are too dangerous or will cause too much injury. What tends to cause more of an injury is what the standard calls a quasi-static contact. This is a constrained contact. So the example I'm going to use is the operator's got his hand on the table, and the robot drives or goes to pick up the component, and the operator's hand gets in the way, and the hand's trapped between the gripper, the end effector, and the actual table, and it's trapped. So this type of impact can be quite high, and it can be quite a long duration. So this is where an injury can occur. So standard also mentions some guidance. So it will have tables, as you can see here on the right, and these tables list out different types of impact, the duration of the impact, and also the forces that can apply for those impacts. And I've mapped it out for different parts of the human body. I've highlighted the hand in my example, so I've brought it out here. So the hand can have a maximum force of 140 newtons in that type of impact. So how do you know what the impact's going to be? Well, the standard recommends actual testing on the machine. So you can buy sensors on the marketplace that look like the ones on the left-hand side here, which the robot is driven into. So it has a load cell at the bottom, which is connected to a PC to gather the amount of force that's applied. We have a spring that's going to apply a nice uniform force and a constant force, and then a rubber pad at the top that's designed to mimic the human skin. So the recommendation is you take a number of positions within the machine that these collisions are likely to occur at, and you physically drive the robot into this device and then use the computer to measure the result. And the result is typically what you can see here on the right-hand side, where the initial impact is quite large, and then as the duration of the impact continues, it will drop down to a more of a sustained level. And this is where this data here is what you compare to the tables that I showed you on the previous slide. If the green line here, as you can see, was within the red or within the white area, it passed the test. If it was to go into the red part of the diagram, it's failed the test, so you'll need to do something to mitigate the size and the duration of the impact. And the best way of doing that really is to slow the process down. So again, that's going to affect the cycle times that you can get from the system. The standard also recommends that there's some annual testing done to make sure nothing's changed on the process, because you never know what could have changed over a year of the machine in production. So what was the reality? What did the customer end up deciding to do? Well, they decided that they needed a bit more cycle time from the machine, and for safety reasons, they decided to put an area scanner to protect the operator and the robot from any of these collisions. So they're now moving from what was a power and force limited exercise to a safety rated stop or speed and separation monitoring process. The area scanner, again, needs to be set up so there's a wide working area to guarantee that the robot is stationary when the operator comes within the collaborative working area. So the footprint of the machine is actually increased quite large now. And now we're no longer in a collaborative style of working. We're actually moved across into this cooperative style of working. So you've now got a choice of robots. Which one do you want to go with, the industrial robot or the collaborative robot? So what did the final machine look like? Well, here's a picture of it. So what the customer ended up doing is actually trying to get that footprint back down. And the way to do that was to install some fixed guarding around 3 sides of the machine. That had the advantage of being able to do high-speed operation and minimize the cycle times as much as possible. They wanted that cooperative way of working. So how did they achieve that? Well, they had an open guarded area at the front. And instead of a physical guard, they used an area scanner to detect the operator coming in to swap over the tray of components. And when that was activated, the robot would stop. So therefore, they decided to actually go with the industrial style of robot in this exercise. They of course now have a wide variety of different robot options to choose from. The other advantage really was there's no risk of impacts between the robot, or the risk of impact between the robot and the human were reduced. So there's no need for that costly and time-consuming impact testing, and no need to repeat that impact testing every year as part of the process. And again, it's reduced the risks of any kind of injury. This was the first machine they were doing of many, so they wanted also a future-proof solution where they can have different types of robots at different parts of the process, doing different safety functions. Some would need no collaborative working and use a true industrial robot. Others, they wanted a fully collaborative in power and force limitation. So going with a robot manufacturer that can supply both technologies really meant there was a lot of consistency and uniformity across the whole kind of range, and they could choose the right product for the right application on their process going forward. So what would I say were the keys to success in this application? Well, the first part is really the planning. Planning how to install the robot safely and thinking through all the options. There's a lot involved with the risk assessment and different risk elements. It's not just the engineers that need to be considered, it's other factors. So assigning who's going to be responsible for that risk assessment is also key. Talk to people who had experience. They came and talked to us because we've done a lot of applications with collaborative, cooperative, and also industrial robotics. So they can pull on that experience that we have. The other thing to consider is looking for an external safety consultant. Once the machine has been designed, why not get an external safety consultant involved early doors to review that process while it's still on paper. If you install the machine and then later have to go back to retrofit some of the safety constraints, that's going to be a lot more time consuming and affect the size and actual footprint of the final application. And these are all services that we offer as part of our system service department. So that was just one application. We get people come to us with all different types of application. I'm just going to look now at where I see them as an industrial application or whether or not they're a collaborative or cooperative way of working. So firstly, looking at the industrial applications. So these are things where there's going to be some kind of environmental conditions. So painting's a typical one, where there's a lot of flammable, explosive gases in the environment. The goal here is really to remove the human from the process completely if possible. So that's really a truly industrial application. Same as work in foundries or particularly hot environments. There's a high risk of burns. So again, keeping people out of that environment as much as possible is the key. Packaging machinery, high speed throughput is key here. High precision is needed. So again, as soon as you mention speed, you're thinking of the industrial robot arms, and you want good guarding to make sure that process is as safe as possible. Moving now on to the cooperative way of working. So this is things such as screw tightening. This is where you've got a screw that you're putting into the product to attach the casing or covers of the device. The screws themselves inherently have a sharp point at the end, and the screwdriver bit will also have quite a sharp bit. It's very hard to minimize the duration and force applied by that if there's any kind of contact. So if the operator is around the environment, it's best to stop that process. There are collaborative screwdriver assemblers in the marketplace, but they tend to be a lot more expensive than a standard screwdriver. So again, a cooperative way of working is often implemented in this technology. My worked example, I looked at machine loading and unloading. So I've covered a lot of the points here. Again, you can choose either style of robot, really. It's all about the cycle time that you need to achieve, and also what's best for your particular application. Looking at bin picking. Bin picking is where we're going to feed components into the machine. Instead of using a bowl feeder or some kind of abrasion table, we're actually using a 3D scanner to detect the component from a mass of components, and then use the robot arm to pick up that component and then place it into the assembly process. Again, you tend to want a lot of flexibility from this system, but you need to consider the cycle time. How many parts do you need to load into the machine at any time? So again, you can go down either path of this type of application, but it's maybe tending slightly more towards the industrial cooperative way of working. Similarly to the bin picking is packaging. This is where we need to put a product into the box. You tend to want a system that's very simple to program, but you need that cycle time. You need to keep up with the production of the components and the assembly of the boxes. So you need that flexible way of working at high speeds when no one's around. But if somebody does need to be involved with part of the process, maybe dropping in some documentation for a special customer, that you've got that cooperative environment to work within. So where do collaborative robots come into play? Well, the key really is to assist that worker. So we're talking about short run assembly tasks maybe, or assembly tasks that you can split the labor between the robot and the operator. So in these scenarios, you might have the robot doing the mundane common components, the simple tasks, and the operator working alongside doing the more complicated or more dexterous, or the tasks that are more suited to that person or that operator. And the most common one and the one that really is best suited for the collaborative robots, I see it as an inspection system or quality control. This is where you have a camera mounted to the end of the robot arm, and you're moving it around the workpiece, looking to make sure all the components, all the screws were assembled correctly in the component. This is ideally suited for a collaborative style of robot because there's no physical contact between the camera and the device. The camera is usually mounted at quite a distance, so it can get a good field of view of the part that's been assembled to take its image. So there's no risk of those quasi-static trapping impacts with this type of applications. So that's one of the key areas for this type of robotic arm. So going back to that original diagram I put up, where you had the industrial robot and the collaborative robot, and this middle area, the cooperative working, you can see there's some applications where you'd naturally always turn to the industrial robot for. They tend to be the highest speed and the high risk applications. There's some that you'd clearly go to for with a collaborative robot, which is assisting the worker and working within the same space. And that cooperative area is really quite a wide variety of applications where you've got to choose the right robot for the right job. And there's many factors to consider depending upon what the process is. However, it isn't just safety that you need to consider when you're looking at putting a robotic system together. It's also the integration of the other components. So it's the robot. It's how does the robot talk to the programmable logic controller that is maybe running the rest of the machinery control. So systems such as our IQR, where you can embed the robot controller into the PLC rack, really helps maximize the amount of data and the speed of that data can get to the robot arm, giving you the most flexible process. Often you'll find a HMI to start and stop that machine and that process. And that HMI is really the window into the machine, not just giving you start and stop information, but also diagnostics information, such as the quality of the components that you're manufacturing, the cycle times, and error codes and information that's going on in the process. So good integration between that and the PLC and on to the robots is key. Looking down from the robot, often when we look at our machining tool tending application, you want the robot to not just tend one machine, but maybe unload the part from machine A, move it into machine B. So you'll need some kind of travel axis or linear slide It's going to link those two machines together. It's a good integration between the robot arm and the servo drive that is driving that linear axis is fundamental and key as well. I mentioned getting data into the HMI, but it's also passing that data and that production information up into the rest of the technology infrastructure, into the enterprise layer, and now more commonly up into the cloud, so it can be analysed and processed to give you the best quality information as possible. So good connections there is also key. And if you fancy finding out a bit more information about our solutions to edge and cloud connectivity, why don't you revisit one of our previous webinars that covered edge computing and cloud technology. So how do we as Mitsubishi address this question of collaborative and cooperative robots? So we've tried to give you a scaled solution. So we've got a 4-level approach here. So we've got a standard range of robot arms that come with standard safety functions to go within that caged environment. That's your typical application. That's your level 1. What we can add to that robot though is what we call MELFA Safe Plus. So MELFA Safe Plus is a safety device that will move the robot from being inside the cage to that cooperative way of working. So it enables the robot to be safely stopped if the operator goes within that collaborative working space. So that's level 2. Level 3 is where we put that sensing device. So instead of using a light curtain, we're actually going to use a soft skin that covers the body of the robot arm. And that skin is touch sensitive. So if the robot operator does touch the robot arm, it comes to a safe stop before any injury has occurred. And it's also a soft cover, so it absorbs as much of that impact as possible. So that's level 3 with the soft skin. And finally, level 4 is our MELFA ASSISTA collaborative robot arm, and that's designed to meet the 15066 safety standard. So that's got the force and power limiting functions built in. So you can see here a real scaled approach where you can take any of our industrial robot arms and use them in a cooperative or collaborative working environment. So just to summarize everything as I've been discussing, we don't really see collaborative robots as a competition for industrial robots. We see that more of a complementary technology. So you can use them alongside your industrial robots to give you the optimum performance, to use industrial robots where they're most effective, so high position and high cycle times, and use collaborative robots where they're most beneficial, which is alongside the human operator working in the same workspace safely. So thank you for your time today. That draws the fixed part of the presentation to a halt. I'm just going to have a quick look through the comments and see if there's any questions that have come through as I've been talking. So if you can give me a second while I just check through what people have said. I've got a question here that's come through, and it says, where did I get the safe speed of 250 millimeters per second from in my worked example? So that speed of 250 millimeters per second isn't actually stated within the safety standard TSO 66, sorry, 15066. It's become the industry standard that the maximum the collaborative robot can work out when working with next to somebody, that's the maximum speed it can work at. What we tend to actually find in these applications is the robot will actually run slower than that, because to get through the testing, you did the force impact testing. The way of reducing the force and duration of that impact is to slow the robot arm down. So they tend to run a lot slower than that in actual applications. Okay. Another question here is it the robot or the application that needs certifying to TS 15066? Well, it's actually the application that needs certifying, not the robot arm. Although some manufacturers, such as ourselves, have actually gone to the lengths of certifying the robot to the standard in a known application, so that we know we can meet that standard if it's implemented correctly. Okay, so that's all. I'll answer the rest of the questions that have come through offline, if that's okay. I'll email you all individually. So I'm just going to wrap up now. So first thing to remind you that is we have another presentation next week on predictive maintenance, so don't forget to register for that one. And then I'm going to play out with a short video that is going to show what the future development is of cooperative and collaborative robots. So this is where we're working with a partner company called Real-Time Robotics, where their technology offers a 3D system that has detected any operator or any areas the robot can't go into, and will calculate in real time the path the robot will choose to avoid the collisions. And this is really the optimum process, is preventing those injuries through avoiding the collisions, as opposed to allowing the collision and then trying to stop safely. So I'm just going to play out that video here. So again, thank you very much for your time, and I hope you all have a very good bank holiday weekend.